Okay, so I'll do it again. I have to select one of these. In this case, we are connecting the supply to this element. Okay, so we supply here the air at a temperature, and then in this unit, we heat up or cool down the air. If it's winter, we heat up the air here, and if it's but the air is healthy. So the most important thing is that the air is coming with healthy conditions, without particles, with the right amount of relative humidity from the air handling unit. And in this device, the only thing we do is to heat up or to cool down the air. But we have to set the right CFM. So in this case, it's 80 for the office spaces, 200 for the lobby, because we have 4 people here and 10 people in the lobby. The same thing we have to do with the return diffusers. We need as many return diffusers as supply ducts or diffusers. So if we click here in this one, here we can set, in this case, we have a default value of 500. Be careful because the default is 500. So in this case, it's 80. So we have to select all these diffusers, and we need 80 here. The return diffusers, 80 and 80. And this one in the lobby, this one has to be 200. Okay, so we need, it's not always like that. We can have a difference between the supply flow and the return flow. Yeah, there might be sometimes in which the supply and the return are not exactly the same. There shouldn't be a huge difference. But the most important thing is that if everything goes well, now we click the first supply duct here that comes out from the air handling unit, the supply or the total flow here should be 520. Why not 520? Because if we have 200 plus 4 times 80, the result is 520. Okay, so if everything is correct, the supply flow, 520, should be the same as the return flow. So this is 520. Yes? Of course, because you did something wrong. Okay, so we have created colors. It's here, project browser, families, duct systems. In duct systems, we can select exhaust, return, and supply. If we right-click on supply, for example, and you click on type properties, we can edit the graphic. And here we selected solid and red. Okay, so that's why we have red for return or in blue for supply. I know the color code can be whatever you need, but if there's a difference between the supply and the return things, so now we are not, and if you do, is that either you are daltonic and you can tell the colors, or you don't know what you are doing at all. Okay, so but if we want to connect the blue thing to the blue duct, that will make sense. Okay, so let's continue. We have fixed the airflow. Okay, so we have typed the correct airflow on each different element. This total supply airflow has to be the same. Where is it? Here. If the airflow is 520, it has to be the same as the return. It's 520. Okay, so if we are doing this, that means that all the connections are correct. And now we can, well, yeah, so that's the minimum thing that we need to know about systems, okay, that we need in small commercial buildings, well, in big commercial buildings, we need air handling units, but depending on the size, we need more air handling units. In this building, we visited the systems, and there are like 4 air handling units in this building, okay? So what's next? we talked about ventilation, and this is ventilation. The ventilation is the air supply that is controlled. We supply air at the conditions that we want. It's fresh air. It has the right relative humidity. It doesn't have particles because here we have filters, and we can get rid of all the outdoor particles that we might find and are dangerous for our health. So the air that we are supplying is healthy air, and then we have to heat up or cool down. So that's why we supply this to this element. Okay, so we supply air at the temperature. If it's not the correct temperature with those elements, we can heat up or cool down that air. Then we have to get rid of it. And so this is what we need. And I'm asking you to do that because all these machines take up space on the roof. So the next thing we're going to do today is to place the solar collectors. Because what's the goal of this exercise? Remember that last week you submitted, or you should have submitted, a report like this. Okay, so here we have the requirements. Here we have all the building data, the wall area, roof area, the total envelope area, total floor area, the volume, all that stuff. We calculated this peak cooling and heating load from Revit. Okay, so we did this with Revit, not with this file that we're working with, because Revit, when we are, why can't we do this with Revit? Because look at this, we are going through the roof. Okay, so we are going through the roof with a pipe, and Revit doesn't like it because that means that we have perforated the roof. So that will affect the space that we have created there. So that's why we use a different file to do this with, to do the mechanical system with Revit. We don't simulate it. Anyway, we did this before. And then those are the passive house standards with the annual, with the cooling and heating peak load. Okay, so we have to make sure that these values, if we divide this by the floor area, then we have to make sure that we meet those requirements. This is the analysis. So we didn't meet the requirements for the peak heating load. And we were far away from the requirement. It's 3, and it was around 40, the peak cooling load. Okay. And then we need the annual energy. So we have the annual energy. We have the limits here. In this case, it's 10.6. Our annual heating demand is 14. We're not far from that. And the cooling demand, it was 10.2, and our cooling demand was 10.2. So that's the only requirement that we can meet. Okay, so that means that our building is not a passive house standard. Is that a big deal? If the passive house standards is mandatory in the state we're working with, it is a big deal because basically they don't give us permission to continue with the process. So we cannot, yeah, so this design doesn't meet the requirements. So we have to change the design. But if we go farther, I think we can do something that it's even more interesting than meeting the passive house standards. Meeting the passive house standards is great because it means that our building has a very low energy consumption. Perfect. But if we introduce renewable energies in our buildings, and now we can make up for the energy consumption. So if we produce the same energy that we are consuming, that's the concept that I think it's more interesting, is the zero energy buildings. The balance between the energy that we consume and the energy that we produce on site, it's zero, or it's even positive, even better. So we have to integrate renewable energies. And how much energy do we need? Well, we have this nice table. We need energy for heating, we need energy for cooling, and we need energy for lighting. So if we can supply this amount of energy with renewable energies, we have a zero energy building. It's even better than a passive house building. If we only have a passive house building, means that our building, it's very efficient. But if we have a net zero energy building, it means that our building produces as much energy as it consumes. And I think that this concept, it's more interesting than just meeting this cold number of the passive house standard. Okay, yes, we are far from meeting the peak cooling load. But what if I provide the building with renewable energy? I think this concept is more interesting than reducing the peak cooling load. And the only way we can do that is by reducing the size of the windows. And well, if I like big windows because I need the solar energy, I need natural light, I have outstanding views outside. So why do I have to reduce the size of the window if I can do something different? So that's the concept of what we're going to do now. The problem is that what is the area that we have available in our building is the roof area. The whole roof area, no, because we need those machines here. Is that the only thing that we need on the roof? Well, if we are working with these split units, if you remember, there was another thing that we need to run the split system. We have the indoor units. So what do we have? What else do we have? No clue. You break my heart. We need in systems, mechanical equipment, we have to select the heat pump. Okay, so here at some point, okay, so we have the heat pump. Heat pump splits, it's split system. The system that we're using here, it's an electric system. It can be different. We can use a hydronic system with a boiler and then radiators or whatever. But if we are heating up and cooling down the building with this indoor electric unit, we need a heat pump. So it's a split system. We have an outdoor unit, the indoor unit. So we have to place those on the roof. So let's select the smallest one. And we have to place this thing on the roof. And we need to place, well, let me see where it is. Okay. Select this, change the level to level 12. And level 12, I think it's yeah, so we have to move it up. Offset, let's say 2 feet. 2 feet and 6 inches. There you go. Okay, so it has to be on the roof, and we need as many outdoor units as indoor units we have here. So if we have 5 indoor units, I have to copy this 1, 2, 3, 4, and 5. Okay. So now the next step would be to connect this to each indoor unit with a pipe. We're not going to do it, but we have to, okay? I just want you to be aware of the space that we need on the roof. We need the air handling unit. And if we are using this split system, which is the most probably convenient thing we can do, because a hydronic system, we can do that, it's very efficient, but to heat up water and to move the water inside the building, well, we need pipes, and it can be more complicated. This is probably the easiest way in terms of connecting things and in terms of understanding how the system works. We need an outdoor unit, and we have to connect this outdoor unit to this indoor unit. And then we need the air handling unit there. So this is what we need to provide ventilation, cooling, and heating to this building. Okay, so now what's left? Okay, we have the rest of the roof available for solar panels, for PV panels. And now we have to calculate the production of our PV array. And if the production of the PV array is the same as the energy consumption throughout the year, now we are close to the zero energy building. So that's what we are going to do today. So we're going to try to analyze the amount of PV panels that we can place on this roof. Okay. Remember, when we are working with systems, we use the mechanical discipline. Okay, so in this mechanical discipline, we can't work with the traditional elements that we have in Revit, and we can select anything. So now we have to change because we're going to work with the architectural discipline. So we can go to the discipline here and change from mechanical to architectural. And now we can select the roof. Okay, so here we see the roof, and we see all the devices that we have on the roof. So I can't place PV panels here. Well, I made that decision first. Where do I place all these elements? They can be scattered, but it doesn't make sense. Okay, so if we organize this, if we leave a band here at the end of the building, at the end of the roof, for all the devices that I might need, I think I have all these space for the PV panels. If I start placing things here and there and doesn't matter, okay, so that's why I have organized this a little bit. And what is the criteria? When it comes to the PV panels, the orientation is the most important thing. So if we click here in Revit, here, this menu that we have at the bottom of the screen, we have the level of detail. Those are the graphic. The third icon, here we have a sun and a light bulb. So click here and select sun path on. Okay. And in this sun path, we see the sun path, of course, and we see the orientation. So this is important because we need to know where the south is, because it doesn't make sense. I mean, we have to select the right orientation for the PV panels. The PV panels are quite expensive and they work well if they are facing south. If we have the wrong orientation, it's not working placing PV panels. We're spending a lot of money and we're not getting anything from it. So what did I do? What was my decision? I'm going to place all these close to the north facade or the north part of the roof. Basically, this is what this building is doing. So that's the south facade. This is the north, and all the machines, if you remember, are in this part of the building. Okay, so they are all in the north facade, and we free the south orientation for the PV panels. Okay, so okay, so I did this because I need to know that we are facing the orientation of the PV panels that I'm going to place. It's south orientation. Okay, so now we have different options. So for the PV panels, basically we have two options. In this building, you see that we have a huge PV array, and that PV array is detached from the rest of the building. We have a structure, and then we have the right orientation for all the panels. This is very efficient, and probably they did this because it's the most efficient way to do that, to make the most of the solar panels. It's quite expensive because we have to build another structure at the top of the building. We need to build a different structure. There's something that it's easier and cheaper, but probably not as efficient. So we can place the panels because we have a flat roof. A horizontal orientation is not the best in terms of solar efficiency. So we need the tilt, okay? Because the sun, as you can see, it's if we look at the sun path, by default, I have here September 22 and 4 p.m. I can change this to today is February 28. The year, it doesn't matter. Okay, so this is February 28th, and this is 9 a.m. okay, 9 a.m. So this is this. If we had sun, we don't have sun today, but the sun today would be at this position. Okay, so this is February the 28th, 9 a.m. So the sun is at this position. If we move this to 12 p.m., the sun is here, okay? And you see the angle of the sun. So the most efficient way to place the PV panel is a perpendicular angle. So if this is the angle of the sun, we need a perpendicular panel here. Okay, so the most efficient orientation for this, it would be a line perpendicular to this line, to the sun path. The sun moves throughout the year. Well, actually, it's the Earth that rotates around the sun. But what we feel is that the sun is moving, and the sun is not always at the same height on the horizon. If we change this is February, if I change the month, if I type here 3, you see that the sun has changed. Okay, so this is March the 28th. If I click here, if I do this in June, number 6, so in June the 28th is there. So we see that the angle of the sun is different, okay? So this sun is almost perpendicular to this. So I have to make a decision because I can't change the angle. Well, I can do it, but again, it's very expensive. I can't change the angle of the sun. So the highest position on the horizon, it's in June, and the lowest position, it would be in January or in December. It's better in December. Okay, so that's the sun angle. So that means that in December, the panel should be almost vertical. In June, the panel will work well if it's almost horizontal. So we have to make a decision, and that's why if you in this, it depends on the location. Okay, it depends on the latitude. We are in Northeast, the United States. So something around 40 goes well. Okay, so if we have a tilt of 40 degrees, it works. Like that's the roof, and that's the PV panel. Something between 30 and 45 degrees, it will work with this angle. Okay, so that's what we're going to do. We're going to place PV panels there. We don't have to insert a PV panel family. We're going to use the easiest option. So when we're going to create a tilted roof, and then we're going to understand the amount of sun that we can get, or the amount of electric energy that we can get if we placed PV panels on that roof. Okay, so let's do it. We are here, we are in this right view, okay? And now I need to place PV panels here. And the angle, it can be, we're going to try 30, and then see what happens. So we're going to go to architecture. We're going to select roof, but roof by roof. Where's the roof here? Roof by extrusion. Okay, so by default, we have roof by footprint. We're going to select roof by extrusion. So select roof by extrusion. We have to pick a plane. Okay, so click OK and hover the mouse and make sure that this rectangle is highlighted here. And then click. And now we need a line. So we need this line. You see that here we have the length and the angle. So what's the length? Usually PV panels are, yeah, so 3 to 4 feet is the usual length of a PV panel. So let's select something 3 feet and 6 inches and make the angle 30. Okay, so something like that. 3 feet 6 inches, angle 30. So let's do this. And then click OK. And well, we have something horrible here. Let's create edit. Let's click here, edit type, because I want to this roof. Here you have structure, edit structure. It's 1 foot. A PV panel, it's something very thin. Instead of 1 foot, let's make it 1 inch. There you go. Okay. So I want something that it's the thickness is 1 inch, the tilt is 30 degrees, and the length it's around 3-4 feet. I don't mind. So even if it's not 3 feet and 6 inches, I don't mind. And if the angle is not exactly 30, I don't mind, but kind of. Now, if you select this thing, well, it has to go from this side to that side of the building. So do you have something like that? No? Okay, so once we have this, when I have copied this PV, well, this PV array, I have copied this roof. The distance between these different rows, it has to be enough so that they are not casting shadows on the next row of panels. Okay, so that's the limitation that we have. And we have to leave that space for all the equipment and the mechanical systems that we have to place on the roof. So Revit has an option, and it's not a very thorough analysis. It's not very reliable, but to understand if we are doing well or we are very far from this goal of the zero energy building, I think Revit is good enough. So to do this, we have to go to Analyze. So if you go to the Analyze tab, you need to have these two, the lighting and the solar options. Do you have these two icons here? Top right hand of the screen, lighting and solar. Okay, so let's select solar. So if we select solar, we have this menu. Study type by default is custom, but we have to select solar energy annual PV. This is what we want. Okay, so we have to select some surfaces, and we have to so the result of this will be the solar energy, the solar annual energy that we can get. So solar energy, surface, it's not, let's select user selection because it's not all the exterior surface. We have to do the user selection. We have to click this here. And you see that by default, we have all the roofs, okay? This is not correct because we don't need this horizontal. So if you hover the mouse here, you have this minus sign, click, and we want to select only the PV panels. Okay, so we have selected only the surface in which we will place the PV panels. And okay, so once we have done this, this is not, we can't click here, so we have to finish. This is tricky because we can't keep going here. We have to click finish first. And now we have selected 99 square meters. Revit, we are using imperial units in Revit, but to create all these calculations, we need kilowatt hours because this is electricity, okay? So electricity, we don't have BTUs. It has to be kilowatt hours. And so that's why Revit works with international units. So we have selected the surface. We have the settings. If we update, let's see what happens. Whoop. So that's all we need. Now we can take a screenshot of this because again, this has to be part of our report. So let's take a screenshot of this. And we can, the following step, we have to add a slide to the report. And this is the solar production of this option. Okay, so we have placed 1, 2, 3, 4, 5 rows of PV panels. We have maximized the length of these PV panels. And that's the outcome. We have 99 square meters. And we have 22,941 kilowatt hours per year. So what the hell is that? Okay, so that's why now we need to come back to this, to the energy demand. Okay, so this is the table that we got from Design Advisor. And those values are energy, it's kilowatt hours per square meter. Okay, so that's the energy consumption. So I'm going to open a new slide. So energy consumption. We can copy this. We have heating, cooling, and lighting. Heating is 44.5. So we can say that heating is 44.5 units are important, kilowatt hour per square meter. Cooling is 32.3. 32.3 kilowatt hours per square meter. And finally, lighting is 5.5 kilowatt hours per square meter. Maybe your numbers are different, okay? But if we are dealing with the same buildings, the numbers should be similar, that it doesn't have to be 44.5, maybe it's 42.7 or whatever. But it has to be something like that. So that's the energy consumption. But here in Revit, we don't have the information per square meter. We have the total energy production. So we have to turn this into kilowatt hours. So what's the, so I have to multiply times the area. What area? The floor area. So what's the floor area in my building? It's 1,800 square feet. So area of the building, floor area, is 1,800 square feet. And now I have to turn square feet to square meters. So square feet to square meter. If I have the 1,800, it's around 117 square feet. So it's one square meter, sorry, 167 square meter. Okay, so now I have to multiply this times 167 square meter. So I have to multiply everything by 167 square meter. So what's the total heating consumption in kilowatt hours? It's 44.5 times 167. So this is 7,431 kilowatt hours. So what's the total cooling? It's 32 0.3 times 167. So it's 5,394. And finally, the lighting, it's 5.5 times 167. So this is 918. So what's the total energy consumption? It's 918 plus 5,394 plus 7,431. So this is 13,743 kilowatt hour. So that's the total energy consumption. So what's the total energy production? With the value we get from Revit, 22,900. Are we good or you need help? Okay, but yeah, look at this first and answer this question. Are we good with those numbers? Yes, we're good because we produce more energy than we consume. Okay, so we have designed a zero energy building. Look at this. We don't meet the passive house standards. Okay, so it's wrong. We don't meet the passive house standards. But if we maximize the roof area, so the energy production throughout the year, it's more than the energy that we consume throughout the year. So now it's a question of dealing with the budget because it comes at a price. I mean, placing PV panels is not something free. It's quite expensive, and we need batteries that would be even more expensive. We can connect this to the grid. Okay, that's the option that we have in this building. We have the PV array, but we are connected to the grid. So on days like today, we don't have any sun, we don't produce any energy, but we have electricity in the building. That's why, because we are getting that electricity from the grid. We need inverters because we produce direct current and we need alternate current. Okay, so the installation of PV panels of the PV array, it's not cheap, it's expensive. So now, what is the cost that our client has to pay upfront to get this zero energy building? Can we afford it? It's great in the long term because I save a lot of energy, but I have to pay a lot of money upfront. So now this is the things that we have to deal with. So it's a question of money. Creating zero energy buildings. Now we can do it easily. We have the technology, we have the PV panels. The PV panels are more affordable now than they used to be. Yeah, because the market, now we have a lot of PV panels on the market and they are cheaper. We can't do that without first being close to the passive house standards. Okay, so we need the right envelope, we need a high thermal insulation, we need triple glazing, low emissivity. We need all that stuff so that we can reduce the energy consumption. Okay, so we have done this. We can do it even better because we are far from meeting some of the passive house standards. But I think even if we are far from the passive house standards, if we supply the energy that we need with renewable energies, we are good. So that's the outcome of this. I'm going to help you now, and I will try a different option for the PV array, because with this option, we have this production. Can we make it even better? Can we maximize the production by changing the geometry of the PV panels? We'll find out